David Smith here with another Flip Classroom math video. A few tips before we get started. First, remember that you can slow down or speed up the playback if that helps you follow along. You can also pause the video at any point to perfect your notes, or if you want to try the problems before I explain them. Lastly, remember that you could turn on the captions and read my words going along the bottom of your screen. Today's lesson covers a review of Chapter 12, Trigonometric Functions. So I'm going to hit all the topics and let you know what you're going to need to be able to do. Okay? So the first thing we did is we looked at this new fancy way of measuring our distance around a circle, measuring angles. So we ended up with this thing about 2 pi radians equals 360 degrees. Now remember, 1 pi is roughly 3.14, so 2 pi is 6.28. So there are 6.28 radians in a circle. Okay, now one of the first things we did was convert between the two. And the conversion is pretty simple. To go from degrees to radians, you just multiply by pi over 180, and that gives you your radians. And then going back from radians to degrees, you just multiply by 180 over pi. Now, a couple things to know. When you're in degrees, you just have degrees. There's no pi's or anything like that. You might pay attention if there's specific requirements to go to 3 significant figures, then you will need to do that if you're working in degrees. In radians, be aware that if you're asked for exact radians, you need to leave the pi in your answer. In fact, when we get to the unit circle, we tend to just talk about radians in terms of pi, and we don't really talk too much about decimal radians. If you get the prompt to show your answers in radians to 3 sig figs, that's a clue that you need to decimalize your radians and put pi into your calculator and find out some decimal radians. The next thing we looked at was the unit circle. So I want to draw the top half of the unit circle, that'd be quadrant 1 and 2 of the full circle. Now there's a trick you need to remember about the unit circle. It's called unit circle for one reason. That has a lot to do with 1. What is that? Radius equals 1. So the distance from the origin to any point on the outside of the circle is 1. So that gives us 4 points, kind of like cardinal directions. This is the point 1, 0, because we're 1 positive x, and we haven't gone up or down, so the y-coordinate is 0. The second point here is 0, 1, because we've come up 1, but we haven't gone left or right anything, so that's why the x-coordinate is 0. And in the same way, this point is negative 1, 0, and finally down on the bottom, I haven't drawn that quadrant, but we have 0, negative 1. And so these are the 4 easy points to get on the unit circle on the outside. Now we'll take a look at the other points in a minute. First, I want to talk about the angles. So we typically divide the unit circle up by 30-degree angles and by 45s. So this first angle is 30 degrees. This second angle here would be 60, and this would be 90. So that's the first way to slice up the unit circle. 30, 60, 90. Now, remember, 180 is halfway around. If the full circle is 2 pi radians, then 1 halfway around is pi radians. In the same way, a quarter way around, or 90 degrees, is pi over 2 radians. So here we go. We've got pi over 2. Pi over 2 is really 3 pi over 6. So if we want to divide that into 3, we're going to have 1 pi over 6, 2 pi over 6, and 3 pi over 6. And here we go. We've got our 30 degree, that's pi over 6. We've got our 60 degree. Pi over 3 is really 2 pi over 6. And pi over 2 is really 3 pi over 6. So we have 1 pi over 6, 2 pi over 6, 3 pi over 6. And we continue on around the unit circle in 30-degree increments or in pi over 6 degree increments. So you should be getting pretty familiar with all these different fractions and reducing them down. Now let's take a look at the 45s. Again, as a reminder, 90 degrees is pi over 2. So 45, which is half of 90, is going to be pi over 4. So another way to count around is by 45 degrees. Each one is pi over 4. So we have 1 pi over 4, 2 pi over 4 is just pi over 2. The next 45 would be 3 pi over 4, and this would be 4 pi over 4, which is indeed just pi. So let's summarize. All right, so now I want you to get a little practice counting around by 30 degrees, but I want you to do it in radians. So I've put out the first 180 for you. 1 pi over 6, 2 pi over 6 is pi over 3, 3 pi over 6, pi over 2, 4 pi over 6, which is just 2 pi over 3, 5 pi over 6 does not reduce, and 6 pi over 6 is just pi. Now I want you to pause the video and take us all the way, the rest of the way around in radians. Okay, let's see how you did. We started here at 6 pi over 6, or just pi. So 7 pi over 6 does not reduce. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 goes to 5 pi over 3. 11 pi over 6 stays the way it is. And 12 pi over 6 is just 2 pi. All right, let's do the same thing, but now we're going to count around by 45s, or pi over 2 radians. So I've done the first 4 for you. We have pi over 2, which is our 45. Then pi over 4. Then we have 2 pi over 4, which is pi over 2. That's our 90. We go another 45, which is 135. That's going to be 3 pi over 4, does not reduce. And then finally, when we get to 180, which is 4 45s, we've got 4 pi over 4, which gives us just pi. Now I want you to keep counting around, get all the way back around to 2 pi, and then come back. Okay, so starting at 4 pi over 4, or 1 pi, we have 5 pi over 4, 6 pi over 4, which reduces to 3 pi over 2, 7 pi over 4 cannot be reduced, and 8 pi over 4, which is just 2 pi. So now we've counted around the unit circle both by 45s and by 30s in radians. It will be super helpful for you if you could do that. Now there's one more piece that goes with this. All right, so now we need to figure out our XY values for these oddball points. Remember, the XY values for these 4 that you have, those are super easy. They're just some combo of 1 and 0 or -1 and 0. So those should be no-brainers, but these 3 points are a little bit more tricky to figure out. So I've come up with a little system that should help you remember it. There's really only 3 values that you need to remember, and it's kind of nice. They're all over 2, so that's simple. And here's a nice little pattern. It's 1 over 2, root 2 over 2, and root 3 over 2. So it goes 1, 2, 3. So if you can remember that, then you can populate your XY values as you go around. Okay, there's just one little tricky bit. Cosine comes first, okay? But cosine starts here with its value and moves backwards through the list as a countdown. So cosine, if we wanted to fill in our cosines, it's root 3 over 2. Now sine counts forward through the list. So that would be 1/2. Then we get to the middle, and the middle is the same. We're counting forward for sine, backwards for cosine, so they meet in the middle. So this one is just root 2 over 2, comma, root 2 over 2. And that leaves the last one to be 1/2, comma, root 3 over 2. So that's a way that you can use to remember which values go where on your unit circle. Okay, so to get the values all the rest of the way, all you have to do is reflect. So this point over here, we're just going to change the value of the x-coordinate. So this is going to be -1/2 root 3 over 2. Remember, y is the up and down, and so y, as long as we're above the x-axis, y is positive. But now we've shifted to the left of the y-axis for this one, so this goes to negative. In fact, all the cosine values are going to go to negative down here, so we'll have minus root 2 over 2, root 2 over 2, and then finally this one over here is going to be minus root 3 over 2, comma, 1/2. And so if you memorize the first quadrant, then you can pretty much do the rest. So if you'd like to take the time, go ahead and sketch your unit circle down to the bottom and fill in all your values. I just want to put in a plug for the unit circle. If you need on the test, you could sketch your unit circle and put your values in. The actual act of doing that primes your brain, makes you ready for the test. You know the unit circle is not in the formula booklet. So if you can make one and use it, then that will help you do a lot of problems. Here's a trick for remembering what sign to ascribe to those three basic values we talked about on the last board. All silly turtles crawl. Perfect. So all means all functions are positive here. Okay, so sine and cosine are positive. And then I want to remind you, tangent is just sine divided by cosine. So we know that both sine and cosine are positive here. So if you divide a positive by a positive, you're going to get a positive. So cosine is also positive here. So that's all. For all functions, all three functions are positive. Silly means that sine is the only one that's positive. And that makes sense. We know that cosine is negative because we're left of the y-axis. And if cosine is negative and sine is positive, this fraction is going to be negative and so will tangent. Silly turtles, T is for tangent. And we know down here in quadrant 3 that both x and y, or sine and cosine, are negative. Having a negative divided by a negative makes a positive, so tangent is going to be positive in quadrant 3. And then finally in quadrant 4, cosine is the one that's positive because we are to the right of the y-axis. And again, tangent would be negative because sine's negative, cosine's positive. So this fraction becomes negative, which makes tangent negative. All right. Then we spent several lessons looking at trigonometric identities. So the first ones were called Pythagorean identities. And actually, it's just one identity that gets rearranged. So the reason it's called Pythagorean is that sine squared theta plus cosine squared theta equals 1 squared. You don't have to write the squared because 1 squared is 1. So this is the main identity. But we can rearrange that and solve it either for sine squared theta or cosine squared theta. And it would just be 1 minus cosine squared theta in that case, or 1 minus sine squared theta. So these are three versions. Now the trick with using these, sometimes they'll just give you a straightforward value of sine theta and you can solve it for cosine theta. Works great. But sometimes you might be working a different problem and you have to realize that you can do a substitution using one of these and then finish the other problem that might be doing a double angle or asking you to solve. All right, so we had three different double angle identities. The first one is cosine 2 theta. So this is why it's double angle. We're saying cosine of whatever that angle is, but twice that angle. So that one equals 2 sine theta, cosine theta. We also have cosine 2 theta. We have two of them for cosine 2 theta. So when you're solving these or when you're factoring, you need to figure out which one you need to use. This one is cosine 2 theta equals cosine squared theta minus sine squared theta. And this one is cosine 2 theta equals 1 minus sine squared theta. Now, because both of these equal cosine 2 theta, they both equal each other as well. So in your formula booklet, they don't write a second line. They just say equals 1 minus sine squared theta. And that's true. These three things equal each other. All right, let's take a pause for a minute and do a quick little problem that builds on what we were doing in the last two boards and has you do a tricky trigonometric factoring step. Okay, so here's the prompt. Show that cosine 2 theta plus sine theta can be written as this. And so basically what they're kind of saying here is rearrange this equation to make it look like this one. And the trick is to remember that you can do a substitution with one of those trigonometric, those double angle identities on the last board. So go ahead and pause the video and give that your best shot. All right, the first step to this involves finding the correct double angle identity to do your substitution. So I looked at my identities and I noticed that this one allows me to get rid of this cosine 2 theta and I'll only have sine thetas, which is a nice simplification. It will allow me to factor and solve. So check this out. Cosine 2 theta is 1 minus 2 sine squared theta. That's my identity. So I just substituted that I substituted this for that, and I have this function. So now I've just got a slight rearranging to do here. I can just go minus 2 sine squared theta plus sine theta plus 1. And so what I've done with just one quick little substitution, I've changed this to the requested form. All right, the second part of this, I set this equation equal to 0. I used one of the favorite Ivy words, which means hence solve, which is kind of like and then solve. So what I have now is I have equation set equal to 0. I need to solve this. This involves factoring a trigonometric equation. So if you're feeling bold, I'm going to ask you to pause the video, do your steps, come back when you're done. All right, before I go into this, I just want to state we do have a range on this problem. We want our thetas to be between 0 and 2 pi. So we're not going further than just one turn around the unit circle. So some of us have gotten to the point maybe where we can just factor and solve this without doing this little substitution. I'm going to go ahead and explain that. If you understand it, you can fast forward through this part. So what we do is we just let x be sine theta, because then we can substitute in x wherever you see sine theta, and that gives us the quadratic 2x squared minus x minus 1 equals 0. I can factor that down to this, and then finally I can solve each of the mini equations, and I get x equals negative 1/2 and x equals 1. So now I can come back, substitute sine theta back in for x, and get this. So I have sine theta equals negative 1/2, and I have sine theta equals 1. So now we can find our thetas. So I'm going to go ahead and do this in radians and degrees, just so you can see that. Now what you think here, when I have sine theta equals 1/2, what I'm asking is where on the unit circle is sine equal to 1/2, and then where on the unit circle is sine equal to 1, and then of course within 0 to 2 pi radians. So go ahead and pause the video. I want you to think real hard about these and come up with my possible answers for theta in radians and in degrees. All right, you may not need to do this, but I find that sketching a quick little unit circle that helps me figure out the exact problem I'm working on really helps a lot. Plus, when I'm grading your test, it's super useful for me to see how you're thinking with this kind of a problem. So, sine theta equals 1/2. Sine theta is the y value. That's the up and down. So I've got to be down by 1/2. So that occurs at 7 pi over 6, or 210 degrees. So that's my first one, 7 pi over 6, which is 210 degrees. And then it also occurs again at 11 pi over 6. That's 30 degrees down, which would be minus 30, but since we're coming around this way, we have to be positive. So it's going to be 11 pi over 6, or 330 degrees. Now this last one, sine theta equals 1, it only happens one time in 360 degrees, or 2 pi radians, and that happens at 90 degrees. We're up here where sine theta is 1, so that's just pi over 2, or 90 degrees. All right, let's do a few more problems using identities. We've seen these in the homework, you've seen them on the quiz. Let's just do another one here. So if sine theta equals minus 1/8, and we're looking for thetas between 0 and 3 over 2 pi, remember that's 270 degrees, or 3/4 of the way around the unit circle. Now we're being asked to find cosine theta. So this is really straightforward. If I have a value for sine, I can find what cosine is. I can use the Pythagorean identity. So go ahead, pause the video, do your plug-in step, and solve this one. All right, here are my steps. I did my plug-in. I squared negative 1/8, which gives me positive 1/64, and I subtracted it from both sides. So that gives me cosine squared theta equals 1 minus 1/64, which is 63 over 64. Now I need to take the square root of both sides. There's my 63 over 64, so take the square root of both sides to get my cosine theta, and it's plus or minus root 63 over 8, and then root 63 simplifies down to 3 root 7. Okay, so now you have to evaluate. The answer, algebraically, is plus minus. That's perfect. However, are both the plus and minus in the range? Pause the video, take a look at that, come back when you have an answer. All right, the answer is yes, keep the plus minus. Check this out. 63 over 64 is almost 1, not quite. So to be almost 1 for cosine, remember cosine is the x value, we've come up just a little bit with a small angle, and we've backed this point a little bit to the right of, or to the left of 1. So this is 63 over 64. And so by the same token, this one is negative. The same thing, negative 3 root 7 over 8. So this is going to be a little bit less than negative 1, but it's totally permissible within our range because we haven't gone past 270, which would be all the way down here. So we're still within the range of this problem. So the plus minus stays. Now, these kind of problems tend to build on each other. So I wrote down our solution to the last one for cosine theta, and now it's asking us to find the sine of 2 theta. So I'm not going to give you a hint. I want you to pause the video, look at your identities, figure out the substitution that you need to make to find this one. All right, so here's my identity. I don't know what sine 2 theta is, not yet, but I do know what sine theta is. I was given that in the beginning, and I just figured out what cosine theta was, which is plus or minus 3 root 7 over 8. So if I do this substitution, remember this is a double angle theorem. We only have one for sine, the other two are for cosine. I can just do this substitution, and now I can do a nice little plug-in step, which is going to be 2 times sine theta, which is negative 1/8, times cosine theta, which is plus or minus 3 root 7 over 8. So now I got two multiplications to do. I can do this times positive, this times negative, get my two answers, and then evaluate my results. So go ahead and do that. All right, so I did my math, and the only difference is the plus minus in here, so I get 6 root 7 over 64, and it's plus or minus. So I did a little decimal approximation because I need to figure out which I get to use. Do I get to use both the plus or minus? Do I have to exclude one of them? So this is roughly a quarter. So go ahead, do your thinking, maybe sketch a quick little unit circle, and decide for me which of those values stays, if not both. All right, I call your attention to my unit circle over here. Plus or minus 6 root 7 over 64. This is about a quarter, so we're about a quarter of the way up to 1. Remember, we're talking about sine, so we're in the y value. So we've come up a quarter. That's our value for our plus 6 root 7 over 64 is right there, and our minus is right there. Now it's pretty clear to see from this one that the minus does not fall within our range, because we're in the fourth quadrant, which is beyond 3 pi over 2. So for this answer, we just have 6 root 7 over 64. All right, let's take a look at the forms of the equations, and then we'll go look at the graphs. So check this out. The equation forms are very much the same. I just substitute sine, cosine, and tangent. So we have a sine b times x minus c plus d. And we just substitute in cosine and tangent. So when you see equations written out, they are in this form. If you don't see a number in front of the sine, that means it's a 1. If you don't see a number for the d, that means it's a 0. Okay, so things like that. All right, so let's take a look at what the a, b, c, and d stand for. A is amplitude for cosine and sine. And that's just the amount that the function goes up above the principal axis or below the principal axis. Okay, so that's amplitude. Now tangent, A affects the curviness of the graph. We did not dive into that very deeply in the exercises, so don't sweat that. Now B is our period modifier. It's not the period. So whatever you see there, it's not the period, but it can be used to find the period. So for sine and cosine, the period itself is 2 pi divided by the b. So if I give you the period, you can find b with this equation and vice versa. Now for tangent, it's period equals pi over b. So it's slightly different, but there's an easy way to remember that. The period of the native sine and cosine function is 2 pi. And indeed, the period equation uses 2 pi. For tangent, the period is 180. Remember, that one repeats every 180 degrees, or pi. So that's why pi shows up there. Finally, we have our horizontal shift. That's our minus c in there. Tricky spot there. If you see a negative c, like negative 3 or negative pi over 2, that means the function is shifted in the positive direction. Okay, so you have to kind of go opposite of that. Lastly, our vertical shift, totally straightforward. If you see a plus 5, it means the function is shifted up 5. So by shifted up 5, what it means is that the principal axis is shifted up 5. So you can think about that. You can think that this d number is really just the principal axis. That's another way to look at that. All right, so the next section dealt with graphs. And I'm not going to cover all the transformations because then this video would probably be a couple hours long for all those different ways to transform. So you are going to want to look at your notes, look at the exercise problems, perhaps review the videos to see how that works. I'm going to cover the basics here and actually provide you some practice. So what I'd like you to do is sketch the sine curve for 0 is theta is less than 4 pi. So that's 2 full cycles of the sine curve. I'd like to go ahead, this would just be y equals sine theta. So go ahead and pause the video, make that sketch, come back. All right, here's your basic sine graph. It goes between 1 and negative 1. That's the amplitude of our function. It repeats itself every 2 pi. That's the period of our function. So I've got 2 full cycles in 4 pi. Our principal axis, that's the horizontal line about which the function is equally spread up and down. That one is y equals 0. Okay, so we have all of our attributes. There's our basic sine function. All right, now I'm going to have you sketch your cosine graph. So now I've written it, instead of theta, I've put my x in there. Now my range is a little different. We're going from negative 2 pi all the way to positive 2 pi. So pause the video and sketch that graph. Here you go. So now I've got it in my negative land. Remember, cosine starts at 1 and drops first, comes back up, does a full cycle from 0 to 2 pi. It just doesn't quite look the same as the sine function does. And then it just repeats itself going backwards. So here we have 2 full cycles of cosine from negative 2 pi to 2 pi. All right, let's finish up with tangent. So now I'm asking you to graph tan x when x is between negative 2 pi and positive 2 pi. Now this is a tricky graph. So remember from the video and what we talked about in class, the best thing you can do for tangent is sketch your asymptotes first, because then that shows you how to draw that crazy curve that is tangent. All right, so I'm going to reason this out with a unit circle. Check this out. Here's my unit circle. Remember, tangent is sine divided by cosine. So tangent has asymptotes when cosine is 0, because we have 0 on the bottom of a fraction. You can't do that, it's undefined. So cosine is 0 at 90 and at 270, or pi over 2, or 3 pi over 2. So those are the 2 places in our first pass around the unit circle. Similarly, if we go negative, it's going to have an asymptote at negative pi over 2 and negative 3 pi over 2. So what I did is I scaled my axes in increments of pi over 2, because that's where my asymptotes are going to fall. And so I know I'm going to have an asymptote right here at pi over 2, and I'm going to have an asymptote at 3 pi over 2. And then I'm going to have an asymptote at negative pi over 2. And I'm going to have one more at negative 3 pi over 2. Now the other way to remember your asymptotes is that they occur every 180 degrees. And again, that makes sense. As cosine goes around the unit circle, it hits 0 at 90, and then 180 later, and then 180 later, which is just pi radians. So you'll see that these asymptotes are related by pi radians. Okay, so now, if you haven't already sketched tangent, go ahead and sketch tangent. All right, so here's the wacky tangent curve. It approaches the asymptote down here in negative land, comes up, goes right through 0, 0, and then gets bigger and bigger and bigger as it approaches the asymptote here. Now, how do I know it's not going the other way? It's simple. If you look at what's happening as you get closer and closer to 90 degrees, or pi over 2 radians, the bottom of the fraction is getting very, very tiny. The top of the fraction is approaching 1, but the bottom is getting very, very tiny. So when the bottom of a fraction is tiny, the overall value is very large. So that's why this one is going up towards positive infinity. So that gives you the graph. And then, just like all the other trig functions, it repeats. It's just not continuous. It doesn't repeat from here. It starts back down here in the negative and does the same old thing. It also goes right through the midpoint between the 180 degrees that separates each repetition of tangent. So I went through the origin, I went through pi radians here, and I went through minus pi radians there. So now, I want to ask you a question. Is my graph good, or do I need to add something else? Okay, something else is right, because my range is minus 2 pi to 2 pi. I haven't done that. So if you haven't noticed that, I want you to pause the video and finish your sketch. Okay, so over here, it's going to come away from this asymptote and start doing the same thing it's doing here, only it's going to stop at 2 pi. That's as far as we get to go on the positive side of our range. On the negative side, it's going to repeat this part of our cycle at minus 2 pi and continue up to this asymptote there. So that's the full graph of y equals tan x from minus 2 pi to pi. Okay, just a few more pieces of advice before I let you go. Make sure you know your formula booklet. There are useful things in there. Know how to find them nice and quick. Make sure you set up a few things that you might want to jot down once the tests start. Maybe you want to jot down the first quadrant of the unit circle with the key values that we talked about earlier in this video. You might want to jot down a few other notes or a few other tricks that you use to memorize certain parts of the tools that you need that aren't in the formula booklet. Finally, make sure to come to Extra Help if you need it and do the review problems. Good luck on the test. Let's see you kick some butt. Now that you've finished watching the video, take a moment to jot down any questions you have so you can bring them to our next class and get some help. You can also watch the video again to perfect your understanding. If you enjoyed it, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.